In this lab, we'll explore a few concepts related to interference and diffraction. A good place to start is with superposition, since we'll need to understand that when we have multiple wave sources, the wave amplitude at any point is simply the sum of the individual wave amplitudes. In this lab, the multiple sources will be either multiple slits placed in front of a laser source, the many grooves in a diffraction grating CD or DVD, or the reflections from the many layers of a thin film. The important point in all of this, though, is that the way in which these waves add depends entirely on the phase difference between the waves we're adding. If the phase difference is a full wave, we'll see constructive interference. If it's a half wave, we'll observe purely destructive interference. If the phase difference is something in between, we'll measure something in between constructive and destructive. We will see that these phase differences arise when the distances to each of the wave sources fit different numbers of wavelengths, or because of the phase shifts that happen when light reflects from a medium with a higher index of refraction. The effects of the second source of phase differences will be quite striking when we look at thin films. By the end of this lab, we should be able to answer questions like, what determines the fringe spacing when we interfere two sources? How does the fringe separation change when we change the source separation or the wavelength or the distance to the detector? And how are diffraction and interference related? Let's move on to the experiment. In this lab, we'll examine the interference of light from two narrow slits, the grooves of a diffraction grating, CD or DVD, or from the layers of a thin film. We'll start with the double slits. Let's take a quick look at the equipment we'll use for this experiment. All of our optics snap into place along a set of rails. At one end we place a laser diode and at the other end our detector. The detector is on a translation stage, so we can move it perpendicular to the rails. We'll use this in the first part of the lab to measure the spacing between interference fringes, and in the second part to measure the diffraction angle from a grating. To align the setup, place an aperture in front of the detector and turn on the laser. Now adjust the alignment screws on the back of the diode mount until the laser passes through the aperture. You may need to adjust the height of the detector to maximize the photodiode signal in Data Studio. Now remove the aperture and insert the multiple slit wheel 1 meter from the front face of the detector. If you put the white plate in front of the detector, you'll see the double slit interference pattern. Try the other settings on the slit wheel and make sure you understand how the resulting patterns differ. To measure the fringe spacing, sweep the detector across the pattern by slowly rotating the wheel on the translation mount. We'll use Data Studio to collect and plot this data. Let's move on to many slit interference or diffraction, from a grating with 1,000 lines per millimeter and from the grooves of a CD and a DVD for comparison. Go back to our previous setup and place the diffraction grating in front of the detector. In the forward direction, you'll see three beams, the undiffracted or zero-order beam in the center, with a first-order diffracted beam on either side. You'll also have beams reflected back from the grating, so be sure to block these with an aperture. We'll measure the distance between these diffracted beam spots by translating the photodiode and looking at the signal in Data Studio. We'll then be able to calculate the angle of diffraction. Measuring the angle of diffraction from a CD or DVD is a little different, since the diffracted beams are reflected. We'll tape the CD or DVD to the white screen and place it in the laser beam path. We'll want the laser to hit the CD at a place where the CD's grooves are up and down, so the diffracted beams come back both in the horizontal plane. We'll then just measure the spot separation with a ruler and calculate the diffracted angles. In this last part of the lab, we'll take a look at thin films, which are made up of many layers with different thicknesses or indexes of refraction. Because of this, different colors of light are transmitted or reflected differently. Our thin films are iridescent sheets of plastic ribbon and art glass. Note how the colors appear to vary across the surface. To observe the interference effects fully, hold the pieces down and look at the reflection from the ceiling lights. Then, light them from behind and note the difference in transmitted color.